Okay, so let's keep going here. We just solved question 7.32. Now we're going to talk about alcohols for a little bit. But way back in chapter one, we covered all the functional groups. So you guys all know what an alcohol is, right? You have a hydroxyl attached to some kind of R group. And we can have primary alcohols, secondary alcohols, and tertiary alcohols. Just as a reminder, so if we have, a methylene and then a hydroxyl, that would be primary. If you had a methine and two R groups, that would be secondary. And if you have three R groups attached to your alpha carbon, that would be a tertiary alcohol. So tertiary. And we see different reactivities between primary, secondary, and tertiary alcohols. So it says here, alcohols can also be used in substitution and elimination reactions and used as starting materials to make alkyl halides. So check this reaction out. I bet you could figure this one without my help whatsoever. You know that a hydroxyl group is a poor leaving group. Okay, poor leaving group. So how do you get a substitution reaction occurring here? Because bromide can't come in and just do a nucleophilic attack like this. Okay, that's a heresy. That wouldn't happen because hydroxide is not a good leaving group. So how does this happen? Well, the answer is HBr is a strong acid. Strong acid. And so it can protonate the alcohol, and you see that on the bottom. So what we end up doing when we protonate our alcohol is we take a poor leaving group and then we protonate it and we convert it into a great leaving group. I'll just put here good leaving group, right? Is water a good leaving group? Yes. Water is the conjugate base of hydronium, and hydronium is a strong acid. So yes, water is a very good leaving group. So good leaving group, right? So there you go. So that enables the bromide to come in. We do our SN2. We have our nucleophilic attack. We have our loss of leaving group. And there you go. So that's why you can take a primary alcohol, treat it with HBr, and you end up with a primary alkyl bromide. Now, what if you have a tertiary alcohol? Will it work for that? Well, let's take a look. It says the mechanism is either going to be SN1 or SN2, depending on your substrate. Yes, a primary alcohol is going to react via an SN2. So I'll put here, see previous slide. But if you have a tertiary or a secondary alcohol, it's going to react via an SN1. So we see here with the tertiary alcohol, yes, the first step is still taking a poor leaving group and converting it into a good leaving group, but it's SN1 at a time, right? It's not a concerted process. First, we have our loss of our leaving group, right? Water is a good leaving group. And then we have our nucleophilic attack like that, okay? So there you go. So strongly acidic conditions, we call these protic conditions. And at the very end of this chapter, I'm going to talk about protic and aprotic a little bit more. And protic conditions are going to favor SN1. I mentioned that to you earlier on. But since primary carbocations are too unstable to form, primary alcohols are always going to react via an SN2. Okay, there you go. So another reaction, and this is one of my favorite reactions in all of organic chemistry, okay, is this reaction right here because it works so darn well, is that if you take an alcohol like this one here, this is terbutanol, and you just put it in some concentrated sulfuric acid, right? It doesn't get any easier than that. Just dump some sulfuric acid into your reaction and then cook it up. What happens to you when you get hot? I know what happens to me when I start getting really hot. Let's say I was to go outside today and start working in the yard or something. I'm going to lose some water, okay? So when you heat up a molecule in concentrated sulfuric acid, it's going to push water out of the molecule. Well, if you drive water out of this alcohol, what are you going to end up with? You're going to end up with an alkene. So that's an elimination reaction. And this is an important mechanism for you to know. What's the function of that sulfuric acid? Remember, sulfuric acid is aqueous, so that means the major acid in the solution is not H2SO4, it's H3O plus. So the first step is going to be a proton transfer to take your poor leaving group and convert it into a good leaving group. Then after the leaving group leaves, then a water molecule can come in and it can abstract a proton, and then we end up with our elimination product. So the thing about this reaction is that you always end up with the most stable alkene. So yeah, the thing about this reaction that's so great is you always get the most stable alkene. So I'll just pencil it in here. Most stable alkene. Of course, in this case, there's only one possible alkene that can be formed. So now what it's asking you to do here is draw a plausible mechanism for the following transformation. So I'm going to redraw the substrate, which is going to look like this. So here's our alcohol. I'll put in the lone pairs. The first step is going to be a proton transfer to convert that poor leaving group into a good leaving group. So we've got our HBr, right? And we're going to get a proton transfer to convert the poor leaving group into a good leaving group. So that's step one. And I know I need to do that because I'm starting out with a tertiary alcohol. So you can either write it like this, kind of condensed like that, or if you want to be, if you want to show every bond in gory detail like that, that totally works too. They mean the exact same thing. So now, again, you've taken a poor leaving group and you've converted it to a good leaving group. And so now the leaving group can just leave, like just get out of here, you leaving group. So it's going to leave, and we end up with a tertiary carbocation. Hello. So now we have a tertiary carbocation. And so what's going to happen? We have bromide kicking around because we lost it in the first step. And so now the bromide is going to come in as a nucleophile. And you're going to get a nucleophilic attack here. There's no chiral center to worry about. So you're only going to get one product. In this case, no stereocenter, so I don't have to draw any dashes or wedges. And there you go. So that's a reasonable mechanism. And make sure you're able to draw a mechanism like this. This is just an SN1 mechanism between a tertiary alcohol and HBr. Let's just see if we can come up with a mechanism for this one. Because you notice that here there's a change in the carbon skeleton, right? This carbon has 1, 2, 3, 4 carbons, but now it's only got 1, 2, 3. So something happened along the way here, okay? But we know we're starting it with a crappy leaving group, and it's being converted into a good leaving group because we're in concentrated sulfuric acid. So let me redraw the molecule. So we started with this molecule where we have our hydroxyl, like this. What's the acid that's going to do the protonation? Remember, you're in concentrated sulfuric acid. You have an equilibrium between H2SO4 and water, and the equilibrium is going to lie to the side of hydronium in the hydrogen sulfate ion. So it's going to be H3O plus that's going to do the protonating. So let me see here. How would I do this? Let's do it in this direction, I guess. We're going to put our hydronium ion. If you drew sulfuric acid, technically it's not correct. It's not incorrect, but H3O plus is going to be more present in the solution. So we take our poor leaving group, we convert it into a good leaving group. Then if the leaving group leaves, we end up with a secondary carbocation, which is going to undergo a methide shift. So that's going to shift over so that we end up with a tertiary carbocation like this. And so what's the last step to get to my alkene, right? If I want to get to my alkene, which is this guy here, okay, what do I have to do? I'm going to have to abstract this proton. And so water will be my base, right? I formed water in the first step when that lost a proton. So a water molecule is going to come along and it's going to pick up this proton, and we're going to form the double bond like that. And that gives us the alkene. So there you have it, a couple of mechanisms for you. So what's our synthetic strategy? If you're sitting there in your chair at home and you're wondering, what's the purpose of all of this? Why do I have to learn all of these reactions? You know, I already passed General Chemistry 1 and General Chemistry 2. Why have to memorize all these reactions and learn about SN1 and SN2 and E1 and E2? Well, the reason why is because organic chemists use synthesis to make valuable, complex compounds from something cheap and readily available. Okay, if you're wondering what's valuable, so it could be something that, you know, maybe might make a material, but I would say, you know, some of the most valuable compounds are ones that are going to save lives. Okay, saves lives. Okay, cures diseases, cures diseases. Okay, so medicine would be, I would think, some of the most valuable compounds, and a lot of them are very complex. So the final product for the first one was this compound, and the final product for this one is this one. Does that? Yeah, good. Okay. So that's why a good organic chemist has to know a lot of reactions. So what have we done in this chapter? We've taken alkyl halides and we've done so many different things. We said you can use cyanide as a nucleophile, right, to do an SN2, right? And if you did an SN2, then you take your alkyl halide and you end up with a nitrile. What if you had an acetate? So this is an acetate ion here, okay? An acetate ion is this. Could that be a nucleophile? Could that do an SN2? Like this, nucleophilic attack, loss of leaving group? Sure. And if you did that, you'd end up with an ester. Could you use a sulfhydryl anion to do an SN2? Yes. That would give you a thiol. Could you use methoxide to do an SN2? Sure, we did it a bunch of times. That would give you an ether. Okay, so all of these reactions over here, all of these, okay, these are all, maybe I could do a better, something like this, this, and this, and this, right? These were all SN2 reactions, okay? This one here is also an SN2 reaction by treating a primary alkyl halide, so this is primary, with sodium hydroxide. Then we said you could take it and treat it with HBr, right? Convert the poor leaving group into a good leaving group. We said you can take the alcohol and convert it into a tosylate. We said you could take your tosylate, you could treat it with a hindered base, right? This is a poor nucleophile, so you're only going to get elimination. We said you could take the primary alkyl halide, treat it with a strong base poor nucleophile, and you could get elimination, right? So we learned a whole bunch of different reactions you could do with a primary alkyl halide, and then we said if you have a tertiary alkyl halide, like this here, okay, we saw the relationship between that and a tertiary alcohol, because if you take a tertiary alcohol and you treat it with HBr, you get the tertiary alkyl halide. You can do eliminations. You can get a Hoffman product with a hindered base. You can get a Zaitsev product with an unhindered base. You can cook the tertiary alcohol with concentrated sulfuric acid, which is going to give you an alkene, right? We said you can make a tosylate from that, which is a good leaving group, et cetera, et cetera. And so we've covered a lot of reactions with tertiary alkyl halides too. And so if you're stuck in a synthesis problem, if I ask you a question, you know, I want you to go from A to B and tell me, how do you do that? Okay. When you're thinking about making something, sometimes you don't know what the first step is. So first step, you're just, what is the first step? I don't know. But a lot of times in this class, you can say, what about the last step? Okay, and you can kind of solve the problem backwards. And when we do that, we call that retrosynthetic analysis. It's kind of a backwards approach. All right, let's say I asked you to make this ether. Okay, I said, I want you to make this ether. Well, you know that really the only way you could make this is via an SN2 from an alkoxide like ethoxide, and then the alkyl halide, right? So you'd need a 1, 2, 3, 4, 5 carbon alkyl halide. So you see that here. So we have pentyl bromide or 1-bromopentane and sodium ethoxide. You put those together, you're going to get an SN2. The retrosynthetic analysis or retrosynthesis arrow is this. It's two lines like this. That's a retrosynthesis arrow. That arrow is specifically reserved for retrosynthesis. And so we'd say you can make this ether, here's the retrosynthesis arrow, from this alkoxide or this alkyl halide. Either one is fine. Both of those approaches will work, but it's a backwards way of solving a problem. And then you see here that somebody really spruced it up by putting in a solvent, because they said that DMSO, which stands for dimethyl sulfoxide, is a polar aprotic solvent. Aprotic, and polar aprotic solvents are best for SN2 reactions. So same thing here. If I asked you, how would you make this compound? Well, you could take the acetate ion, right? We said that an acetate ion is a good nucleophile, and you could react that with ethyl bromide, right? Because that's going to do an SN2, nucleophilic attack, loss of leaving group. So there's a lot of different things that we can make now. So before we solve these problems here, I want to take a look at these in just a second. But before we do that, the last section just deals with solvent effects, I think. Yeah, this part here is like the last page of content. Really, all you need to know is that polar aprotic solvents are best for SN2. So we use these guys for SN2, whereas polar aprotic solvents are best for SN1. And I went over this with you before, but what a polar protic solvent is this. If it's polar protic, obviously it's polar, but it's capable of hydrogen bonding. And so you see in all the polar protic solvents, you see capable of hydrogen bonding, all of them. Whereas if you look at polar aprotic solvents, none of them have a hydrogen bond, right? There's no H bonds in any of these. And so what are the protic solvents? Water, alcohols, acetic acid, ammonia, right? These are all capable of hydrogen bonding. But what are some polar aprotic solvents? I'm just throwing these out at you because you should have heard them at least once. Acetone, which is nail polish remover. DMSO, which is dimethyl sulfoxide. Dimethylformamide, I mentioned that today. Acetonitrile is this compound here. And the last one is HMPA. But again, I don't worry about my students using these a ton on quizzes. It's more about just knowing, did I put them in the reverse order? Oh, I put the wrong thing here. Sorry, these are best for, where's my eraser? SN2. Just wrote down a heresy. I guess I was just, there we go. SN2 is polar aprotic solvents. So the way that they work is that, let's say you have a nucleophile like chloride, okay? What happens is that in a polar aprotic solvent, the polar aprotic solvent they're incapable of stabilizing nucleophiles. And so what it does is it just raises the potential energy of the nucleophile. So that lowers the activation energy. Whereas they are capable, protic solvents can stabilize nucleophiles. And so they keep them at low energy. And so that's why we choose aprotic solvents for SN2 reactions. Anyhow, this question here, what does it say? It says, for each case below, transform the starting material into the desired target molecule. More than one step may be required. In order to plan a reasonable synthesis, it is a good idea to start with a retrosynthesis. I would say you don't really need a retrosynthesis for these ones, okay? Especially the first two, I'd say no retrosynthesis required. So it's not really the best testing question. But if we look at A and B, you have the same substrate in both. You have an alpha carbon. You have two types of beta protons. You have these ones in blue. You have these ones in red. If I want to make this compound, okay, if I want to make the Hoffman compound, for that, would I use a hindered base or an unhindered base? Could anybody tell me if I want to make the Hoffman product? The one in the black circle. Would I use a hindered base or an unhindered base? Exactly, thanks. I'd use a hindered base. So to make this one, the best choice would be potassium T-butoxide. So I'd use potassium T-butoxide for that. If you just write, like that, that's totally fine. Or if you wrote the Lewis, kind of a bond line structure like this, that's fine too. They all mean the exact same thing. And for the next one, because this was the Hoffman product. For the next one, since I'm making the Zaitsev product, I'm going to use an unhindered base. So for that, I'd use something like sodium ethoxide. So we'll put ethoxide, or if you wrote sodium ethoxide, that's totally fine too. All right. The next one, again, not the best question for a retrosynthesis. I can see a couple of ways of doing this problem, but let me ask you guys this, okay? If I asked you this question on a homework or a quiz, I want to go from this secondary alcohol to this alkene. I'll give you a second to think about it, but does anybody have a strategy of how you would do this reaction? You can see we're making a Zaitsev alkene, but a hydroxyl group is not a good leaving group. So could anybody help me out with a first step for this? How would I convert that hydroxyl group into a good leaving group? It wouldn't be with you wouldn't want to protonate it in this case, because in that case, you'd end up with a mixture of compounds. Okay, we only want to get one compound. So how do I just convert it into a good leaving group and just isolate that? So the best way to do it would be to make a tosylate. Okay, because remember, if you make a tosylate with tosyl chloride and pyridine, then you convert a poor leaving group into a good leaving group. So in that case, you'd end up with this. Exactly. So then if I wanted to make this compound, I've got two types of beta protons. I've got these ones here, and I've got this one here. So in order to make this compound, right, I want to pull off the blue proton. So for that, I would use an unhindered base. So to pull this guy off, I would use something like sodium ethoxide. And that's going to give me one product, that product only. If I used HBr, yeah, it would work, but I'd end up with a mixture of the Zaitsev and Hoffman. But you can see that Arubial has found an even better way to do it, because this way that I've just written down, this is 2 steps. Okay, and there's nothing wrong with the 2-step process, but he's got a better process, which is this. So there we go. If I take that same starting material, in one step, if I just treat that with sulfuric acid and cook it up, just heat the snot out of it, pardon my language, I'm going to end up with the most stable alkene. So that's a one step way of doing that reaction. So both are good. I wouldn't give one better grades over the other, but I like this one more because it's simpler. Okay, I work smarter, not harder, right? It's easier to set up. So with that in mind, let's take a look at the very last, come on, slides. The very last questions that I had put in here were these ones here. I think they're about reaction rate. Yeah, so it says here, which of the following reactions is expected to produce one propanol at a faster rate? Explain. Well, you can see that these are SN2 reactions, right? These are both SN2 because you have a nucleophile, right? It's going to do, you're going to get a nucleophilic attack, loss of leaving group. Just the difference is water is polar protic, and then this one here is DMSO, and that's polar aprotic. Does anybody remember which one is going to give you a faster reaction rate for an SN2? Would it be the polar product or the polar aprotic? It's the aprotic, exactly. So there you go. And for an explanation, you could just say raises the activation energy, or sorry, lowers the activation energy, raises the potential energy of the hydroxide. Either one is fine, but I'll just put here lowers activation energy, okay, by increasing the potential energy of hydroxide. And the last one, again, is another SN2, right? You would have the iodide. So this is an SN2 as well. The iodide is going to displace the bromide. And yeah, it's a crappy mechanism, so I'll leave that out. But anyhow, one of them is done in ethanol, and one of them is done in, sorry, they're not. They're iodide and chloride. Okay. So which one is going to be a better nucleophile? Would it be iodide? It's kind of iodide versus chloride. Which one's a better nucleophile? I'll help you out. This one is going to be faster with the iodide. Iodide, we'll put here, better nucleophile. Chloride's a good nucleophile too, but iodide is better since it is more polarizable. And remember, the polarizable just means it's more able to distort its electron cloud. So polarizable. Okay, there you go. And then for the top one, I'll put lowers activation energy, increase potential energy of hydroxide. And that covers the entire chapter.